Hey guys, this is section 6.6 where we're going to talk about calculating the equilibrium position for a gas phase chemical reaction. So let's look at our generalized chemical equation. Here the lowercase letters stand for the stoichiometric coefficients, capital letters stand for each of the species. We can write this as the sum over I of x sub I, capital X sub I. In my notation, the little x stands for each of the coefficients. The capital X stands for the identity of the species. And in this notation here, the coefficient, the little x, for a reactant is negative and for a product is positive because we're losing reactants and forming products. And so we can say this is mass balance, this sum is equal to 0. We also know that for this reaction to proceed spontaneously from left to right, dG of the reaction must be negative. And when dG of the reaction is 0, we're at equilibrium. So at constant temperature and pressure, we showed this before, dG of the reaction is equal to the sum of the chemical potentials times the change in the amount of each of the species. And now, so we're going to start and let the reaction go just a little bit, an infinitesimal amount to the right, and it changes by epsilon moles, however many moles it changes by. We're going to call that epsilon of some product. It doesn't matter which one. Okay. Epsilon is what's called the extent of the reaction, how far the reaction has proceeded at that point. We can also say that at that point, the moles of each species changes by n sub I, which we could write as the amount that we started with, that's n sub I star plus the coefficient times the extent of the reaction. If we look at the differential form of this, because the amount that we start with, n sub I star, doesn't change, the differential of that's 0, so that goes away. The coefficients don't change, they're constant, so they come out in front. And we get this right here. So dn sub I equals x, this is the coefficient d epsilon. Which means now we can write the dg of the reaction. Instead of this form, what we can do is we can replace the dn sub I with what we just showed. And we get this form right there. And just remember, the mu sub I, that's the chemical potential of that species at constant composition. We talked about that a little while ago. So what we can do, okay, we can manipulate this equation just a little bit. If we take this, move it over this side right here, make that a partial. Looks like this, at constant pressure and temperature. That's equal to the sum of the coefficients times the chemical potentials, which is just, all that is the change in the chemical potential overall. We know at equilibrium, the partial g is going to be 0, so partial g, partial epsilon is equal to 0. We also showed back there in section 6.5 that we can write the chemical potential, again, reversible ideal gas, as the chemical potential standard conditions plus RT ln of the ratio of the pressure to 1 bar, which means that the difference, the delta U, is the sum of the reactants and products of n, how many moles in the balanced equation for each species, times its chemical potential at standard states, plus n times RT ln of this is the mole fraction. So watch out for this notation, guys. This is a chi, which stands for a mole fraction. This is x, stands for a coefficient. Those are different things. So now let's look at this real simple reaction. A going to B, both gases, constant temperature and pressure, coefficients are both 1. We saw that in section 6.5 and section 6.5, we saw that there's going to be contributions to the Gibbs energy, both from the mixed and the unmixed species in the reaction. And we showed that we could write the G, Gibbs energy, the unmixed, as this. These are mole fractions now. And here, the mole fraction of A, because there's only 2 species, we wrote as 1 minus the mole fraction of B, because the mole fractions have to add up to 1. And mixed, we had this. We had the RTL and mole fraction terms thrown in. Same thing, mole fraction of A we write as 1 minus the mole fraction of B. So thinking about that, if we know the chemical potentials and the temperature, then we can use that equation to find the G of the mixed, G of the unmixed, and that means delta G of the mixture, which is a function of the extent of reaction. Now, if we look at this graph, okay, this is this is from your textbook. They picked some specific values. It doesn't really matter what they were. This blue line is Gibbs energy of the unmixed. This whatever gold line is the Gibbs energy of the mixture, and oops, we see that there's a minimum here. That's where the minimum of the Gibbs energy of the mixture, which is where the derivative is equal to 0. It ends up it's at some point. This is the extent of the reaction. That's like 0.76 or something. I don't remember. Delta G, which is the mixed minus the unmixed, looks like this. Its minimum is, for this one, which is, they had, I think, equal molar amounts, was at 0.5. Okay, so what we can say at this point is that we can tell whether or not a reaction is going to be spontaneous, going to proceed spontaneously or not, if we know at that point how much of everything there is. And because they're gases, that means partial pressures usually. Because that's going to change, right? But if we know how much we have, we can't say in general if it's going to be spontaneous or not, because it's going to depend on which side of the equilibrium you lie. We can also say that for small changes in the amounts of the species, constant temperature and pressure, no expansion work, the condition for spontaneity, dG of the reaction is negative, or partial G, partial extent, constant P and T, is equal to the sum of the coefficients times the chemical potentials, which has to be less than 0. At equilibrium, that's equal to 0. This is constant pressure and temperature. If it's constant volume and temperature, then we use the Helmholtz energy, and it's identical basically. Well, it's similar equations. So it's spontaneous at constant volume and constant temperature if dA is less than 0, or partial A, partial extent is less than 0, and at equilibrium if partial A with respect to the extent is equal to 0. So let's look at a little example. We want to see if this reaction is spontaneous or not at 298.15 Kelvin, constant pressure. If we start out with this pressure of each of the reactants, which is I made them the same as each other, 0.314 bars. And because the chemical potential at standard state is equal to the delta G of formation of that species, we need to know the delta G of formation for ammonia. It works out because the delta G of formation for hydrogen and nitrogen is 0, because those are elements in their standard states. So that's just 0, that goes away. So the mole fraction of each of the species is just the partial pressure divided by the total pressure. 0.9442 is just the sum of 3 times 0.314. So it's 1/3 for each of these. So what we want to do is we're going to use this form right here. Okay, plug in, and this is, remember we said this is equal to the chemical potential times the number of moles is plus RT ln of the mole fraction times the number of moles. So this is for ammonia, delta G of formation plus RT ln the mole fraction, which is 1/3 for everything, minus 3. This 3 comes from this 3 right here, that's N, delta G of formation of hydrogen, and same likewise here, 3 RT ln mole fraction of hydrogen, minus delta G of formation of nitrogen, 0, and so on. Plug all that in and check my work, please, as always. I got a negative 8.3 kilojoules per mole. And the important thing about that is that, yes, it's negative, which means that this reaction is predicted to be spontaneous in the direction written under these conditions.